And this week, we are gonna talk about option. So before we go into the option, let's first do a little bit review or go through some little bit details on what we did last week, or maybe it's 2 weeks ago, but I wrote last week. So we talk about the law of one price, or we can call it the arbitrage-free pricing. And the second thing we discuss is the risk-free return rates. And then most importantly, we talk about the future and the forward contract. And then I did a little bit graphing here. Like this graph, you can see the X. This is the S, which stands for the stock price, and this is the P&L. And what this curve or this line shows is the P&L we can gain. And then we see if our stock price goes up, we make more money if we purchase the forward contract or the future contract. And here is the F here is the break-even point. So it's the price of the forward contract. Okay, and then this, just as I mentioned, we all can see this is a straight line. And then this P&L, it shows the payoff of a forward contract is linear. Okay, and then when in the quantitative finance industry, when we say linear, it's actually quite a little bit confusing word, because sometimes if we say linear, it means the payoff of the derivative is linear. It's a line, just like this one. But sometimes when we say linear, we are talking about the partial differential equation. We are saying the PDE is linear. And then when we say nonlinear, it means the PDE is nonlinear. So in this kind of sense, we put option into a linear option. But if we look on the payoff of an option, it's nonlinear. So when talking about linear or nonlinear in derivatives, to be honest, I feel it's sometimes a little bit confusing. We can actually look on the payoff graph of the options here, which we will discuss in more detail. You can see this is a call option, the payoff, and this is nonlinear because it's two lines together, two straight lines together. And then, but the partial differential equation we will not discuss here, but it's something linear. Okay. And then we also will discuss how we can price a future or forward contract, and it's using some non-arbitrage condition, and then discuss and we hope the expectation of the payoff is 0. So that's the arbitrage-free condition. And then we can go directly into options, which is definitely the most exciting part. So by definition, it's saying that the option contract, it gives the contract holder an option, but not an obligation to practice certain right. Okay, so this here is very important here. What is an option? Just as its name, an option is an option, but not an obligation. And this this line here is very, very important. It's an option, but not an obligation to practice certain right. And this certain right can be anything. So it can be a right to purchase a stock at a predetermined price. This is what we call a call option. This right can be to sell and stock for a predetermined price, and this is a put option. It can also be on the maturity date. We say the option holder can decide whether he or she wants to exchange a stock with the other party. For example, I give you the Apple stock and you give me the Microsoft. This can also be an option. It's called exchange option. So the key idea of options here is what this certain right is. It can be anything. So next time, when you talk to other people, don't be when other people ask you hey, what is an option? And you say, okay, an option is at a certain day, I can decide if I want to buy a stock from you. No. So that's a call option. That's the simplest form of option. It's the option that I spent most of my time study when I was in school. But when I started working in the industry, I realized option is way more than that. Option can be anything. This certain right can be anything, and that's why option is so huge. So And then the key here, just let me, I know this is like, I have talked this like several times, but option is an option, but not an obligation. This is like the key idea of the option. And then after we see see like more detail on call option, you will get my point. And call option, it gives the holder the right to buy the underlying asset by a certain day for a certain price. And put option gives the holder the right to sell the underlying by a certain date for a certain price. And then the wording here or the definition here is definitely very like confusing if there's a first time for you to study option. But like I hope if we can see like some examples and they can be like more, at least like more vivid, or you will see like how it functions. So let's say call option. Like we are like trying to fill the gap here. If we assume the underlying be a stock, and then the S is the stock price, ST is the stock price on time T. So S0, which means is the stock price today, and we let it be $100. Okay, so the underlying asset, the price is $100. And a call option, it has a predetermined certain day and certain price. If we say the certain price is 120, and we use a symbol K here, it's called a strike price, and we will talk about the terms later on. And then the certain date is T is equal to 1 year. Okay, so we just fill the gaps. We fill in like these terms. So our option becomes, it gives the holder. So if I buy this option, I become the holder and I have the right to buy a stock after a year for $120. Okay, and at this moment, I have like no idea what the stock price is gonna be after a year. It could be $140. It can also be $90. But no matter what price it goes, I will be able to make the decision if I want to buy the stock for 120. Okay, so here we have two scenarios. The first scenario, the stock price goes 140, and the 140 is greater than 120, simple math. In this case, I'm definitely willing to buy the stock for $120 because the stock itself was 140, and getting it for 120, it worth it. I can make a profit of $20 from this purchase, from this exercise, this option right. Okay, and on the second scenario, if the stock price goes to 90, in this case, 90 is smaller than $120. If I buy the stock from the market, it's $90. I definitely don't want to exercise option. It will be stupid if I can buy the stock for 90 on the market. Why on earth I want to buy like from the option holder, like from the option writer for 120? Okay, so like here, like you can see like why it's called an option but not an obligation. On the maturity date, you can make the decision whether you want to buy this stock for 120, and this is like the certain price that we decided on the time that we wrote this option. So if the price goes above 120, I'm definitely willing to buy the stock. If the price below 120, I just let the option to expire and just go away. I don't care about it anymore because it would be silly if I buy the option for a higher price. And then in this case, the question left is like, okay, we can see like the graph here before we talk about the option pricing. So if we can see the graph here, it's like a cash flow or like a simple graph. We can see here, like today, the stock price I put like here is $100. The first scenario, it goes to 140. And then because we say the strike is 120 and I can buy the stock for 120, I definitely want to do that and I make the profit of $20. If it goes like $90, below 120, I do nothing and I earn $0. And this is, as I mentioned, it's a call option. or mathematically, we normally write it this way, like max st minus 120, 0. So you can see this math equation. If st goes above 120, my payoff is st minus 120. If st goes below 120, this part gets negative, and then the max of this whole thing is 0. So this is like the payoff for a call option, okay? Okay, and then the next question we left is like the call option. If we define a call option like this, like what's the price is supposed to be? If in this like very happy scenario, we know that the option either goes 140 or goes to 90. This is like a binary scenario. It's very simple, and we know it's guaranteed to be either this price or 90, 140 or 90. And then the first question left is here, is like, we know it's gonna be 140 or 90, but we still don't know like what's the probability of going 140 or going 90. So one thing we should know is it cannot be like 100% to be 140, because if it's 100% to be 140, everyone will be willing to buy the stock for 100 US dollars if it's guaranteed to be 140, because it's like guaranteeing you a 40 US dollars like profit. It's like arbitrage. So P here cannot be 100. And then, okay, so as some simple thing, because we said that there are two kinds of probability. The first one goes to 140, and the second one goes to 90. If we say that goes up, the probability is P. Because it's a binary case, the probability of going down is 1 minus P. And these two sums up becomes 1. So this is just like simple probability. And then back to the question, like what exact value this P should be. Okay, here, like the non-arbitrage condition plays in this game again. No matter what value of P should be, one thing we want to guarantee is the expectation on this day is still 100. So there would be no arbitrage. Okay, so because we assume that I assume here the zero interest rate condition I assume. So the stock price today is 100. The stock price in a year, the expectation of the stock price in a year is still supposed to be 100. So I put it here like the so this is like the symbol for expectation. Expectation of ST on S0 is equal to 100, should be 100. Okay, so if you haven't studied probability, this notation here is like the condition. So this whole thing means the expectation of ST given the stock price today is 100. So this is like this part like the meaning of that. So the expectation is supposed to still be 100. So we have probability P to go 140 and then 1 minus P to go 90. So we use P multiplied by 140 plus 1 minus P multiplied by 90. And this is 100 because the non-arbitrage condition. And then we solve the equation and we got a P equal to 0.2. And we know that we have 20% of the probability to go up to 140. And we have 80% of the probability to go down to 90. And when we go up to 140, we make a profit of 20. In this case, we have 20% of the chance to make 20 US dollars. And then we have 80% of the chance to make a zero profit. And the net profit we can make, or the expected profit we can make, is $4. And then this number 4 is gonna be the option price for this option. Okay, and then and of course, option pricing is more difficult than just this simple scenario. And we will like gradually like goes deeper and deeper into like the option pricing. But this is our first step. And this method is called the binomial tree method. And this is the one-step binomial tree method. Do we have any questions so far? Okay, if we don't have any question, I'm just like continue the seminar. Terms. The example that we look at is called a call option. And then we use this equation max st minus k comma 0 to notate the payoff of a call option. And the put option is like the opposite way. It's like on the given on the predetermined day, I can decide whether I want to sell the underlying. So the payoff for me becomes max k minus st. And the certain date in the definition is what we call the maturity date, and we normally use a symbol capitalized T to notate for the certain date, or we can use the notation time to maturity tau, and then this tau is equal to capitalized T minus the lowercase t. If we say the lowercase t is like the time to date. And the certain price is what we call the strike price, and it's the K. Okay, and then there's like another very short and sweet equation called the Book of Parity. If we assume 0 interest rate and no dividend paying, then there is this short and sweet, very nice equation. It shows call minus put is equal to stock minus K. Okay, because we know that the call option, the payoff is gonna be max st minus k0. The payoff of put is k minus st0. If the stock price is larger than k, so let's do this. If the stock price, okay, so if the stock price is larger than k, if we say st is greater than k, this part becomes 0, right? So it's only the st minus k. On the other hand, if we say that st is smaller than k, this part goes to 0. And this part becomes negative k plus st. So it's still like st minus k, right? So you can see like in either scenario that we always have this equation, c minus p is equal to st minus k. And then this is not the exact formula for the Book of Parity because I assumed the 0 interest rate and no dividend pay. But the ST here, if we have some interest rate, the ST becomes F, the forward contract. But it won't be a big issue here. But the intuition is here, and then this is probably the first arbitrage strategy you can think about. So if we see that this condition is not satisfied, if we see the call and the put, their price difference is bigger than S and K. It's basically saying there is some opportunity for us to arbitrage. And this arbitrage opportunity actually existed in the market about like decades ago. Probably you will not be able to make profit from this equation right now because everyone knows the equation. But back to like decades ago, this is probably a very good method for you to make some real like risk-free profit. And then this graph I've showed you like at the very beginning. This graph you can see as like the payoff of the first one is the payoff of call option. And the thing about the option is it's always a little bit confusing at the beginning, like when you think about like who's the buyer of the option, who's the writer of the option, the buyer of a call, the buyer of a put. It's like always like very confusing direction that is going, like you have no idea like what is your exposure to the underlying. You don't know, like for example, if you are a buyer of a call, you don't know like if you are longing the underlying or shorting the underlying. But after like you go like study this for a few days, it just becomes like more handy. And then the first graph, this is a call option, the payoff, and the bottom line is a buyer. which is like the condition like we normally think about. So when you buy the option, you're actually longing the underlying. So when the underlying price goes up, at the very beginning, because it's below the strike price 100, you never want to exercise options. So it's like continuously and here. The reason it's not zero because at the very beginning you bought the option for $10. Okay, so you pay like a negative 10 at the very beginning. And then gradually, like after it gets to 100, gets to the strike, you decide, okay, I'm gonna exercise the option and I'm going to make some profit. And you gradually like making money like up to here. This is a break-even point, 110. The reason is that at 110, you make $10 by exercise the option. And this positive 10 breaks even with the negative 10 you spend at the very beginning when you buy the option. Okay? And then it just like gradually keeps going. And same for the rider. At the very beginning, you make $10 by selling the option to the other party. And then after the strike, after the stock price goes beyond 100, you gradually lose money, and here it's like the break even. What you lose breaks even with what you gain at the very beginning. And the same logic applies here like for the put option. Okay, and then let's go back to the binomial tree pricing method. The first question is, I don't know if you came out like in your mind, like why I put here like 140 and 90. And the answer is, I just made it up because I like integers. I just put 140 and 90 here. And these numbers are not good. So in reality, if we want to price a call option, this 140 and 90 here is definitely wrong. And then the reason is, so first, when we think about the stock price, we assume its return to be normally distributed. If it's a normal distribution, it has an expectation R, and it has a volatility sigma square, or we call the variance. And in this case, at the very beginning, we used the R, right, the risk-free rate. We did the non-arbitrage condition, and then we used, because we assumed R to be 0, so we used the non-arbitrage condition to calculate the probability P to make this whole scenario arbitrage free. But we didn't talk about the volatility, and that is how it comes to play here. Eventually we want two conditions. The first is arbitrage free, and the expectation of these two realization becomes 100 times e to the RT. The second condition we want to satisfy is the variance of these two realization becomes sigma square. Okay, so because you might argue like, why I put like 3 variables here? We normally like notate the price goes up with U, the price goes down with D, U for up, D for down, and P for probability. And you might argue like there are 3 variables here, but I only stated 2 conditions. The first condition is to satisfy the expectation. The second condition is to satisfy the variance. So I can come out with 2 equations, but we have 3 variables. Yes, but to be honest, like the U and D, they don't have to be 2 different variables, because we can assume it to be like a 1 ratio, maybe with Q. And the U is equal to 1 plus Q% times S0. And D is equal to 1 minus Q% times 0. So you see, like we can assume like the U and D, they are symmetric around 100. And in that case, we only need to solve, we can combine U and D, like they combine into like one variable. So in that case, we have 2 variables. One is the ratio of change. The second is P, the probability. and we have two equations, one satisfy the expectation and then another satisfy the variance. And in this case, it's no more 140. It's like the better number. We solve the equation, we get a better number. And now 90, same, we solve the equation. And this will be a better binomial tree. The second question is also like very straightforward, like why one step? The answer is definitely also it's just for simplicity, because like we just started like talking about the option, and then this is like the happy and the simple scenario, and then we are about to look on another example that has two steps. And in reality, the more steps, the better. If we can have like 1,000 or 10,000 or even like 1 million steps, it will be great. But it's gonna be like very calculational expensive. So like for quants, like one job is like to determine like what is a good like trade-off. What is a good number of steps I can get a relatively good result, and at the same time the calculation is not not too expensive. And yes, like when the n goes to infinity, we will have a closed form solution. Okay, and then this is like a binomial tree for two steps. And then you can see like this tree is definitely looks different from the one I drew. This one, most importantly, like when we like normally draw a binomial tree, we put like the stock price on the top at each node. We put the stock price on the top, and below is the option price. So for this is a call option, and the strike is 21. So the stock price is 24.2. And because 24.2 is greater than 21, we exercise the option and we make a profit of 3.2. If it goes to 90.8, we don't exercise the option and we make a profit of 0. And same logic applies here. And then for the node B, we know, so based on the same logic, we can calculate the probability goes up and the probability goes down. And then we can calculate the expectation of we can get the expectation of the option price here. And the same logic, we can get expectation at 0 here, because like no matter it goes up or down, we don't make any profit. I see some chat, just let me. Okay, thanks for letting me know it's recorded. It's now about the lecture itself, so okay, let's keep going. For the node B, we see that the stock price goes to 20, and we can calculate the option price. And for node C, we see the stock price goes to 18, and then we know the option price is 0 for this point. And we backtrack to the node A. The node A, we use 20, 22, 18. We can calculate the probability P and performance P here. And then we do the same, like applying the same logic, we can calculate the option price. And this is like for the two-step binomial tree. And with the same exact logic, we can apply it again. So we can do like 3 steps, 4 steps, 5 steps, 100 steps, no matter how many steps you want. And the more steps, it makes the option price more accurate. Then after talking about the binomial tree method, the next thing we will talk about is the Black-Scholes model. And the Black-Scholes model is like probably the most famous option pricing model that probably everyone who studies option will study the Black-Scholes model. But like just in my personal idea, I definitely like the binomial tree method better for 2 reasons. First is short and sweet, and it's very intuitive. Second, the binomial tree can be applied to all different kinds of options, but the Black-Scholes model can only be applied here for the European vanilla option. I think I'm doing a little bit like spoiling here. I haven't talked about like the difference between European and American option. But just please keep in mind, like so far what we have talked about is all European. And then the Black-Scholes model can be only applied to European options and only applied to European vanilla options. And when I say vanilla options, it means calls and outputs. It's like the vanilla mean. The meaning of vanilla is basically saying it's either call or put. And the Black-Scholes model, it has several assumptions. The first, the underlying stock price, it follows geometric bounding motion. And I will just explain like in 1 second, like the meaning of geometric bounding motion. Second, we have a known and a constant interest rate. Third, we have a known and a constant volatility. Four, we assume that the market is efficient. The market is efficient, so there is no arbitrage opportunity. So we can apply the arbitrage-free pricing method. Second, the second of the fourth bullet point, the assets, they are perfectly divisible. So this maybe looks like very strange, but like if we want to mathematically prove the Black-Scholes model, involves like the delta hedging, and the delta is like 0 point something. It's a number like it's not an integer, so that's why like it has to assume the assets are perfectly divisible. It sounds nonsense, but mathematically it's very crucial here. And then we assume no transaction cost. It's also like it's not realistic, but it's always the case when we try to do some mathematical modeling. And lastly, it assumes no dividend paying. Okay, so this last bullet, so let's talk about these bullets like one by one. Geometric bounding motion, we will talk about like very soon. Interest rate, constant, and known. So we know that the interest rate is definitely not constant because interest rate can be like there are lots of different interest rates, and then they're changing like every day. For example, if we are using the 10 years treasury bond yield as interest rate, it changes like every second. It's not a constant. But the thing is, because we all know that the interest rate is always some number like 1%, 1.5%, like a very, very, very small number. And relatively speaking, our option and normally mature maybe in like the longest option probably matures like in a year or two. It won't be like super long term. So in that case, the impact of interest rate is trivial. And even like in the industry, when people are talking about the sensitivities of the options, everyone's saying like nobody cares about the sensitivity to the interest rate. But on the other hand, the volatility, this condition, the known and the constant volatility condition, is not the case for the real industry. And then we will probably discuss this like maybe in the next seminar. So the volatility, first, it's not a constant, first of all. It's like changing. Like we will see, like even for like same underlying on the same with the same maturity, the options, they might have different volatility for different strikes. And then for options with different maturity for the same underlying, it's also different volatility. So this is like the most interesting part of like the whole the option trading. And people trade the option, and most importantly, is because people want to get the exposure to volatility. So although like we assume in the Black-Scholes model like there's a constant volatility, but it's never the case. So that's why like the Black-Scholes model, it can only be like the textbook solution for undergrad or for like graduate students. It's definitely not a solution for the industry right now. It's like way simpler, but it tells like lots of the intuition behind the option. And then we talk about the fourth bullet point, and then the last bullet point, it says no dividend paying. So this is probably not a very serious assumption here, because even if the stock pays dividend, if it's a continuous dividend paying rate, there is some modification for the vanilla Black-Scholes model. And the modification is like pretty straightforward and pretty intuitive and easy. So for the classic Black-Scholes model, the classic Black-Scholes world, it assumes no dividend pay, but it's not a big issue here. Okay, geometric Brownian motion. It's a geometric Brownian motion. If we say R is a risk-free return, sigma is a volatility, WT is what we call a Wiener process. It's a normal distribution with zero mean and with a variance T. The geometric Brownian motion follows what we call the stochastic differential equation. So if the first two lines, if the first two lines, if it looks like very difficult to you, we just don't look at it. And for these two lines are more like the intuitive way to understand the differential equation. Because if we put in the discrete form, it's basically saying the stock price tomorrow is equal to the stock price today plus a percentage return plus some volatility. If we don't look at the volatility part like right now, if we only look at these two parts, so let's think about like a stock price. It changes every day, and there's a percentage return. If we say the stock price today changed 1%, and the stock price is 100, it means it goes up by 1. And you see, like it's exactly like how it's like the idea here, like this return part. It's like the stock price today plus the stock price today times the percentage return. Okay, so like this is the key idea of the geometric Brownian motion. Like the returns, it's like the percentage return instead of like adding a 10 to the current magnitude. No, but the geometric Brownian motion is like adding a 10%. So if we go back to look at the equation, I hope like it makes more sense like why people are using this method to model the stock price. It's the key idea like inside it, the stock price goes up or down in percentage terms, like 1%, 2%, 3%, instead of like saying it goes up by 1, it goes up by 2. Okay. So, or maybe like if we can more like visually look at the geometric Brownian motion, it might also be helpful. So it's simple like type Google, and then we do geometric Brownian motion, and we search some images. We can see there are like tons of graphs of like showing some simulation for the geometric Brownian motion. And if you look at like those like vibrating curves, I guess like the only thing like if I ask you like what does this curve looks like, you will say it looks like stock price. So yeah, that's like what people are. This is like the way that people are modeling the stock price. Quants or the mathematicians, probabilitists, we use geometric Brownian motion to model the stock price. Oh, and then for the loss term, the epsilon here is like the volatility part, or sigma times epsilon t is like the vibrating part, the volatility part. The epsilon, it's a Wiener process, as I mentioned, or think it as a normal distribution. So each time you move up by a little step, and this step is guaranteed, and it's the R part. After going up by one little step, there's another vibration. This vibration can maybe bring the stock price higher, or sometimes it goes lower. So it's possible, like if you want to draw a curve of the Brownian motion, geometric Brownian motion, it actually goes down. It's possible. But if long-term wise, it's probably going like somewhere going up. But it all depends on like how huge is the volatility, and then how huge is the R. And then mathematically speaking, we say that STF follows a log normal distribution. And then by solving this equation and applying some expectation on probability and integrals, we solve for the vectors model, and then we got this final result. The call option is equal to S0 and D1 minus K e to the negative RT and D2. It's super long, and we look on the call option first. We try to narrow like one by one symbol by one symbol. The first symbol, C, stands for the price of the call option. Cool. Then S0 is stock price for today. It's also something we know. And this symbol N here is a function. It stands for the normal distribution CDF. And CDF means the cumulative distribution function. And the N is in this form as the integral of negative infinity to x with the density of the normal distribution. Okay, and D1 is the input for this CDF. And D1 is equal to this long thing. It's equal to the log of S0 divided by K. K is the strike price, plus risk-free rate, plus sigma squared. Sigma is the volatility divided by 2 times T. T is the time to maturity. And divided by sigma times root T. Minus strike times the discount factor times the normal CDF times D2. And D2 is like this thing, which is very similar to D1. So this equation, even if you don't understand like how it's mathematically derived and why it is, but at least now you look on this equation, if you have a calculator, you will be able to calculate the call option. If I tell you the stock price, I tell you the strike, the interest rate, the volatility, and the time to maturity. So you see, like there are 5 variables you need for this call option to calculate. And it's like the stock price S, the strike K, time to maturity, either tau or T, depending how you define it, interest rate R, and the volatility sigma. And this is also like the same thing that we did for the binomial tree model. For the binomial tree model, if we want to price a price an option with a binomial tree model, we definitely need to know the stock price today. We need to know the strike K. We need to know like when it matures. We need to know the interest rate. And although like the simple example I give, it gives the interest rate is equal to 0. So okay, I give a lazy example, but you see the point here. It has the interest rate R, and we have the time T, and it together gives a discount factor, but you need the R and T together. And then the volatility. And the example I give, it didn't show the volatility. But what is important here? The sigma here. We discussed a little bit like previously. This volatility is a condition we need to satisfy to calculate the up and down value for the binomial tree method. Okay, so a little bit heads up. Up to this point, like all we talk about is all European option, and it's all European vanilla. And not all the options in the financial market is not all European. Some of the options are more likely the options we will see as American payoff is American option. And then how American option different from the European option is European option, you can only exercise the option on the maturity date. But for American option, you can choose to exercise the option any day or any time before the option expires. In this case, it's basically saying like if you are holding the American option to the maturity date, this American option is simply an European option. So in the American option, it's like American option is like it at least gives you the option holder the right as much, at least gives the amount of the right as the European option. So American option is like more powerful than the European option. So it's like more valuable than the European option. Another very important option is Bermuda option. Like, like there's a Europe and there's America, and then Bermuda is like in between of America and Europe. And then that's why it's like geographically it's true. And in terms of option, it's also true. European, you exercise on the maturity date. American, you can exercise any time before the maturity date. But for Bermuda, you can exercise on some predetermined dates. For example, if it can be a Bermuda option, and saying you can decide whether you want to exercise option today or on maturity. And this is exactly the example I will show here. So we have a stock price 100, strike 80, time 1 year, and the interest rate 0 because I'm lazy and never want to do the interest rate. A Bermuda option in this case, we assume that you can decide whether to exercise option either today or on maturity date. Sorry, what I mean is, it's not like if you don't exercise it today, you have to exercise it on the maturity. No, it's like if you don't exercise it today, on the maturity, you can make another decision whether to exercise or not. Okay, so if like in this scenario, if we want to do the binomial tree pricing, if it's European, we did this like last time. I mean, like an hour ago or 40 minutes ago. The stock price today is, I think it's a typo here. The stock price today is, if we say like it's, I think I did some typos here in my notes, but basing on here, it's 110 here, it's 100 here. Yes, and this should be 30. So if it goes up to 110, we get a payoff of 30. If it goes down to 80, we get a payoff of 0. And this is European, okay, in this case. And then if it's a European option, we know the option price is 26.7 based on this probability and the expectation of the payoff. But if it's Bermuda in this case, just 1 second. But if it's Bermuda in this case, I think all my numbers are very messed up here. I will correct the numbers before I share with Chella. But the idea here is, if it's Bermuda, if we decide not to exercise option today, it becomes European, right? Because like the condition I gave at the very beginning is we can either to make the decision today or make the decision on the maturity date. So if we don't exercise it today, it becomes European. So at this point, right now, the decision I will make is A, I exercise the option, and then I get S0 minus K, which is 100 minus 80. Or I decided to continue the option. If I decide to continue the option will be an European option, which worth 26.7 US dollars. I know the numbers I give here is totally wrong, but like the idea is here. Like if I decide to continue the option, it becomes 26.7. And if I decide to exercise the option, I make 20 US dollars profit. You see, in this case, after I decide to continue, it gives me more profit on expectation. So as a rational being, I probably will decide I'm gonna continue the option. And the option price today will be 26.7 because the decision I will make today is to continue it. So for this simple case of the Bermuda option, the Bermuda call for today is the maximum of continuation value and the exercise value. So no matter which value is larger, it becomes the Bermuda option price. And the most like the intuition here is for a Bermuda option, like as simple as this one, to choose to exercise it today or choose to exercise on the maturity, I'm basically today I have to make a decision of whether I continue as a European option or I exercise it and get the money right away. And which one gives which one the expectation gives a higher profit, I decide to do which one. And then that's how I price this option. So in that case, if I realize that if I exercise the option, it probably gives me $1,000 US. But if I continue, it gives me maybe only like $10 US. I will exercise it right away. And this exercise value becomes a Bermuda option price. In this case, if we know how to price a Bermuda option, American option also becomes very straightforward. It's just like more complicated, but the intuition the same. Because if you think about the American option, it's like you can exercise it every second before the maturity date. And Bermuda is like on the dates we predetermine. If we predetermine the dates to be every second, then a Bermuda option simply becomes an American option. So like American option is like the extreme case of Bermuda option. So to price an American option, we just at each second, we make such decision. We want to continue or we want to exercise. And no matter which value is the larger one, it's the value for this second. Okay, I think this is all I have today. Do we have any questions? Um, what's the first line? The 55 US dollars, please. Is a strike?
Oh, by the way, for the people that are going, just as a reminder, the next session is in 2 weeks. But yeah, thank you guys for coming. Anyways, just carry on with the questions, I guess, on the chat. But yeah.
What do you mean by like invoke your option? So do you mean like so okay, so like the case here is because first the option just as it said is like September. So first like the option matures like on September the 24th.